Welcome, and to begin this next video, which is going to introduce the fundamental theorem of calculus part 1, we will take a moment for you to do this exercise on your own. Normally, if we were in class, we do it at our tables or together with small groups, but we don't have those in this setting, so I'm just going to say pause the video, answer it as best as you can, resume when you are ready to see the solution. Okay, here's what I have. First, I think it's important to think about what the function g is. So g is saying it's the area from 0 to this unknown place x, where x is actually determined based on what was put in g. So I think of it as an accumulation area function. So what area has been accumulated under f from 0? That's how I think about it. So then in that light, if we think about f in relation to g, right, we would have to view, so if g is found by the area under f, that means f is the derivative of g. So, and so if we're looking at maxima and minima, right, the maximum and minima is where where g would be changing from increasing and decreasing. Well, that's where the derivative changes from positive to negative or vice versa, right? So specifically if we're looking for maxima and minima, right? If we're looking at maxima are going to be at where it changes from positive to negative, and that would happen at 2 and at 6, right? And then the minima would be at when it changes from negative to positive, so then at 4 and 8. Okay, but it just asks for all of them. So there we go. Where does it attain its maximum value? And I'm sort of cheated by looking at part D to answer this perhaps. But the biggest change from increase to decrease would occur at x is equal to 2. Okay, certainly 6 and 10 are other candidates, but the graph part D kind of helps us figure that out. And you can see the graph that I've shown in green there as well. So that could help too, just as another way to double check. But how I figured it out without the graph was to say, well, okay, 2, 6, and 10 are going to be where the maxima are, and then the absolute, I think it's going to be at 2, because after 2, you're subtracting area, subtracting a chunk of area, adding a little bit back, subtracting more area, adding a little bit back, and so you're never going to get as high a y value at any of the other x values. Where's the concave downward for g? So this is where, okay, if we're doing it strictly based on f, it would be thinking about the intervals of concavity of g would be the intervals of increase and decrease of f. So concave down would translate to the same thing as f decreasing, okay? And so f is decreasing from 1 to 3, 5 to 7, and 9 to 10, okay? So, and then my graph is shown there too. And so all this helps me kind of assemble the graph. But hopefully that pretest went okay. And we're going to extract some of the ideas there to kind of get started about get started on the fundamental theorem of calculus part 1. Okay, and so the big idea in the pretest was to introduce a function that was defined using an integral. And that can happen, right? As I mentioned, this was an accumulation function. We're adding all areas since that solid endpoint. And so if we think about the definite integral, again, geometrically, it does mean that it is the area between the two endpoints. It's just that the endpoints can move. And so if we have a function, right, that is kind of well known, maybe a function, well, at least we can draw a picture of it. Goes down, up, and down like this, right? And we know that this is a fixed endpoint, A, and maybe B is an endpoint over here. Put that as B, okay? But what we're interested in is how the area changes from A to a place X in the function. So we're saying A, or X, can be at minimum, or can't be any smaller than a because then we don't have an area, but it is no larger than b. And we're looking at how the area changes as we change from a to x of this function f of t dt. And I should add in a few more labels here. This was b, and then this would be our function f. Okay, and the t, a lot of times students get hung up on the t. Why is it t and not x? So the variable, what we call it inside the integrand here, this is the integrand, what is inside the integral. The variable in there, when we have a variable in the bound, is really just a dummy variable. Like when we integrate, it just integrates out, right? We have to do, according to the evaluation theorem, we would do, you know, g of x minus g of a, or something like that, right? Adapt the notation, but the variable t would disappear through integration. So whether you use t, I would recommend not using x, but you could use a different variable as well. Okay, so now let's take a closer look at this function that I just defined, g of x, as the integral from a to x of f of t dt. According to the evaluation theorem, right, this was going to be big F of x. And I'm just using f, so big F prime to be the derivative, or big F prime would be f. Little f, I should say. Let's see, then we get f of a like that, right? And then, you know, we would have to say if f is piecewise continuous here as well. Okay, and there is an big F prime equal to little f. Okay, so I mean, yes, we have to address those assumptions, but now calculus as a study is studying rate of change, right? And so what would be the rate of change of this? Well, we could say this is g prime of x. This would be the derivative. So we would need to do d dx of integral from a to x of f of t dt. Okay, which would be d dx of, and we showed from above in the evaluation theorem, this would be f of x minus f of a, right? And then this whole thing, this big F of a, that is a constant, right? So then that means that would just differentiate out to 0, and we'd have big F prime of x, which is just f of x. Okay, and so that ends up being really, really important. So if, again, this is saying we start with a function that's defined in terms of an integral. And then when we look at the rate of change of that, it's just the function that's inside of the integrand with the variable that was in the upper bound put into the function. That's interesting. Okay, so we'll formalize this result in the next video when we study the exact language of FTC Part 1.